following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
Vasily Strela, who works now for Morgan Stanley, did his PhD here in the math department, and kindly said he would tell us about financial mathematics. So it's all yours.
Yeah, so first of all, let me thank Professor Strang for giving this opportunity to talk here, and it feels very good to be back to 1806. So a few more words about myself. I've been Professor Strang's student in mathematics about 10 years ago. So after receiving my PhD, I taught mathematics for a few years, and then ended up working for a financial institution, for an investment bank, Morgan Stanley in particular. And I'm part of analytic modeling group in fixed income division. And what we are doing math applications in finance and modeling derivatives, fixed income derivatives. And that's actually what I'm going to talk about today. I want to show how 1806, a wonderful class which I admire a lot, which applications it has in real world, and in particular in finance and derivatives pricing. And let's start with a simple example, which actually comes not from finance, but rather from gambling. Well, let's assume that, well, let's look at horse racing, or cockroach racing if you prefer. And suppose there are two horses. And sure enough, people bet on them, and bookie is a clever one, very scientific-minded guy, and he made a very good research of previous history of these two horses. And he found out that the first horse has 20% chance to win, and the second horse has 80% chance to win. And he is actually right about his knowledge about the chances to win. On the other hand, general public, people who bet, they don't have access to all information, and the bets are split slightly differently. So the 10,000 is placed on the first horse, and 50,000 is placed on the second horse. Bookie, sticking to his scientific knowledge, splits the odds 4-1, meaning that if the first horse wins, then whoever put on the horse gets his money back, and 4 times his money back on top of it. Or if the second horse wins, then whoever put money on this horse will get the money back and 1/4 on top of it. So let's see. What are chances for bookie to win or lose in this situation? Well, if the first horse wins, then he has to give back 10,000 plus 40,000, 50,000, and he got 60,000, so he gains 10,000. Well, good for him. On the other hand, if the second horse wins, then he has to give back 50,000 plus 1/4 of 50, which is 12,500. So 6,250 altogether, and he loses $2,500. And after many runs, the expected win or loss of the bookmaker is the probability of the first horse to win times the expected win, plus the probability of second horse to win times the expected loss, which turns out to be exactly 0. So in each particular run, bookie may lose or win, but on even he expects, in the long run, he expects to break even. On the other hand, if he would put the chances, he would set the odds according to the money bet, 5-1, what would be the outcome? Well, if the first horse wins, he gives back 10,000 plus 50,000, 60,000, exactly as exactly the amount he collected. Or if the second horse wins, again, he gives back 50 plus 1/5 of that, 60. He breaks even. So no matter which horse wins in this scenario, the bookie breaks even. And how bookie operates? Well, he actually charges a fee for each bet, right? So the second situation is much more preferable for him. When he doesn't care which horse wins, he just collects the fee. While here he may lose or gain money. And this is quite useful observation, which we will see how it works in derivatives. So now back to finance, back to derivatives. So we are actually interested in pricing a few financial derivatives. And what is a financial derivative? Well, a financial derivative is a contract, payoff of which at maturity at some time t depends on underlying security. In our case, we always will be talking about a stock as underlying security, and probably interest rates. What are the examples of financial derivatives? Well, the most simple example is probably a forward contract. Forward contract is a contract when you agree to purchase the security for a price which is set today. You agree to purchase the security in the future for the price agreed today. Well, for example, if you needed 1,000 barrels of oil to heat your house, but not today, but rather for the next winter. On the other hand, you don't want to take the risks of waiting until the next winter and buying oil then. You would rather agree on the price now and pay it in the future and get the oil. What the price should be? What is the fair price for this contract? Well, we'll see how to price it. Well, the few observations here is that this line represents the payout. It's always useful to represent the payouts graphically. This is just a straight line because the payout of our contract is S minus K at time t. And this actually gives the current price of the contract for all different values of the underlying. And usually the price of the forward contract is set such that for the current value of the underlying, the price of the contract is 0. So it costs nothing to enter a forward contract. So that's why it intersects 0 here. What are other common derivatives? Another common derivative are calls and puts. And I put European call and put here. Don't be confused by European or American. It has nothing to do neither with Europe or America. It has to do with the structure of the contract. European basically means that the contract expires at certain time t. American means that you can exercise this contract at any time between now and future. We'll be talking only about European contracts. So European call option is a contract which gives you the right but not obligation to purchase the underlying security at a set price K, which is called strike price, at a future time T, which is expiration time. So if your security at time T ends up below K, below the strike, then sure enough, there is no point of buying this security for a more expensive price. So the contract expires worthless. On the other hand, if your stock ends up being greater than K at expiration time T, then you would make money by purchasing this stock for K dollars, and your payout will be S minus K. And this is the graph of your payout. And this line here, as we will see, is the current price of the contract. And we'll see how to obtain this line in a few minutes. Another common contract is a put. Well, while call was basically a bet that your stock will grow, right? The put is a bet that your stock will not grow. So in this case, the put is the right but not the obligation to sell the stock for a certain price K. And here is the payout which is similar to the put but just flipped. And this is the current price of a put option. Calls and puts, being very common contracts, are traded on exchanges. Chicago exchange is probably the most common place for the option for the calls and puts on stocks to trade. I just printed out a Bloomberg screen, which gives you information about a few calls and puts on IBM stock. So I did it on March 8th, and the IBM stock was trading at this time at 81.14, and here are descriptions of the contract. They expire on 22nd of April, so it's pretty short dated contract. They can go as far as 2 years from now, usually. And here is a set of strikes, and here are a set of prices. And as you can see, there is no single price. There is always a bid and ask, and that's how dealers and brokers make their money. Like a bookie, they basically charge you a fee for selling or buying the contract, and and that's how the money are made. They are made on the spread, but not on the price of the contract itself, because as we'll see in a second, we actually can't price the contract exactly, and there is no uncertainty once the price of the stock is set. There are plenty of other options. A slightly more exotic contract is a digital, which pays either 0 or 1, depending on where your stock ends up. It probably is not exchange traded, also I'm not sure. There are hundreds, if not thousands, of exotic options where you can say that, well, how much would be the right to purchase this stock for the maximum price between today and 2 years from now. So it will be path dependent, depending on how the stock will go. The payout will be defined by this path. There are American options where you can exercise your option anytime between now and maturity, and so on and so forth. So just before we go into mathematics of option pricing, just a few observations and statements. That first of all, it turns out that thanks to developed mathematical theory, if you make certain assumptions on the dynamics of the stock, then there is no uncertainty in the price of the option. You can say exactly how the option, how much the option costs now, and that's what provides. And this is a big driver for the markets. So dealers quote these contracts, and there is a great agreement on the prices. The price of the stock of the derivative contract is defined completely by the stock price and not by risk preferences of the market participants. So it doesn't matter what are your views on the growth prospects of the stock. It will not affect the price of the derivative contract. And as I said, so the mathematical part of it comes into giving the exact price without any uncertainty. So let's consider a simple example now. Let's assume that we are in a very simple world. Well, first of all, in our world, there are only 3 objects. The stock itself, the riskless money market account, meaning that it is an account where we can either borrow money or invest money at a riskless rate R, and finally our derivative contract. Here we are not making any assumptions on what kind of derivative contract it is. It could be forward, it could be call, it could be put, it can be anything. Moreover, our world is so simple, but first of all, it's discrete, and second of all, there is only one time step to the expiration of our contract, dt. And not only there is only one step left, we actually know for sure, we know exactly what are transition probabilities. There are only 2 states at the end, and we know the transition probabilities. So with probability p, we move from the state 0 to the state 1, and with probability 1 minus p, we move to the state 2, right? And just notice, because this is riskless money market account, it's the same in both cases, right? You just invest money, and it grows with the risk-free interest rate. So what can we say about the price of our derivative f? Well, it's simple-minded. Let's start with the forward contract. We know what the payout in delta t of our forward contract will be. It will be just the difference between the stock price and our strike. Well, a simple-minded approach would be, well, we know the transition probabilities. Let's just compute the expected value of our contract, and that's what we would expect to get if there were many such experiments. Well, you take p, probability of going to state 1, you multiply by the payoff at state 1. You take minus p, probability going to state 2, multiply by the payout in the state 2. You sum them up, and you get this expression. And as I said, the common thing to choose the strike such that the contract has 0 value now, so you get your strike. Well, in particular, you could say that if you research the market well and you know that the stock has equal probability of going up and down, then actually your strike, you expect your strike to be an average of two values, end values of the stock. But as we can imagine, following our bookie example, this is not the right price. There is actually a definite price which doesn't depend on transition probability. And here is the reason why there is a definite price. Well, let's just consider a very simple strategy. Let's borrow just enough to purchase a stock. So let's borrow S0 right now and buy the stock for this money. And let's enter the forward contract. Well, by definition, forward contract has price 0 now, so we enter the forward contract. Now, at time dt, when our contract expires, what happens? Well, we deliver our stock, which we already have in our hands, for in exchange of k dollars. That's our forward contract. On the other hand, we have to repay our loan. And because it was a loan, it grew. It grew to S0 times e to the RDT. Now, let's see. What would happen if k was greater than S times e to the RDT? Then we know for sure, we know now for sure that we would make money. There is no uncertainty about it now. Similarly, if k is less than this value, then we know that we will lose money. And that's not how the rational market works. If everybody knew that by setting this price, you would make money, people would do it all day long, right? And make infinite money. So there will be no other side of the market. So the price has to go down. So the only choice for k, the only market implied choice is that k has to be equal to S times e to the RDT, right? And as you can see, it doesn't depend on transition probabilities at all. That's what market implies us. And that's the price of forward contract. And that's actually explains why when I was plotting the forward contract, current price was just the straight line. It's just discounted payoff. The payout is linear, so it's just the parallel to payout. And and that's the idea, basically. The idea is to try to find such a portfolio of stock and the money market account that with such a payout, which will exactly replicate the payout of our derivative. And if we found such a portfolio, then we know for sure that the value of this portfolio, the replicating portfolio today, is equal to the value of the derivative. Because otherwise, you would make or lose money riskless. That's no arbitrage condition. So can we apply it to our general one-step world? Well, so if we have a general payout F, what we want to do, we want to form a replicating portfolio such that at expiration time, it will replicate our payouts, right? So we want to choose such constant A and B that such that the combination of a stock and money market account in both states will replicate the payout of our option. Then, if we are able to find such constants A and B, then we just look at the current price of the contract, and it has to be equal to the current price of our derivative. Well, but in our particular case, this is easy. It's just two linear equations with two unknowns, easily solved, and here is current price of our derivative. No matter what payout is, I mean, you just substitute the payout here, and you know, if you know S1, S2, and S2, that's it. A useful way to look at it, just to rewrite this equation, is in this form, and then notice that actually the current price of our derivative can be viewed as a discounted, expected payout of the derivative, but with very certain probability. This probability is not, it doesn't come from statistical properties of the stock or from any research. It actually is defined by the market. So it's called a risk-neutral probability. So this probability doesn't depend on the views on the market by the market participants. And an interesting observation is that actually the value of the stock, the discounted value of the stock is actually also is expected value of our outcomes under this risk-neutral probability. And that's basically general idea. Now let's move one notch up and try to apply this idea to continuous case. Well, if we live in continuous world now, we need to make some assumptions on the behavior of the stock, right? And a very common assumption is that the dynamics of the stock is log normal. Log normal meaning that the logarithm of the stock is actually normally distributed, right? So here, mu is some drift, sigma is the volatility of our stock, and dw is a winner process. W is a winner process such that dw is normally distributed with mean 0 and variance square root dt. And our approach would be to find the replicating portfolio. And what does it mean? It means that we want to find such constants over time dt. So we assume that A and B are constant over next step dt, such that the change in our derivative is a linear combination with these constants of our underlying of the change of our underlying security and the change of money market account. Now, we just need to look more closely at this equation. And first of all, let's concentrate on df. So f, our derivative is a function of stock value and time, right? But unfortunately, our stock value is stochastic, so df is not that simple. And to write df out, we have to use a famous Ito's formula from stochastic calculus, which actually just tells you, which actually is analog of Taylor's formula for stochastic variables. Well, let's see. If our S will not be stochastic, if it would be completely deterministic and depend only on dt, then there would be no term, and differential of f is just a standard expression. On the other hand, if we have dependence on stochastic variables, then we have to have more terms. And why this happens? Well, in very rough words, is that because the order of magnitude of dw is higher than dt. It's square root of dt, right? So we have to make into account more terms, And in particular, we have to take into account next order of ds squared. And formally, ds squared can be written this way. And again, very rough explanation is as follows. If we would square this equation, there will be 3 terms there. One would come from the square of this term, and which order this would be? It would be of the order of dt squared, next order of magnitude, right? Much smaller than dt. The second term will be cross product of dw dt. What order of magnitude we are talking about? It is dt to the power 3/2, again against much smaller than dt. On the other hand, the third term will be the square of dw, which is of order of magnitude of dt. So that's what we have to keep, right? And that's what either formula is about. Okay. Now we are basically we know all terms here, and let me stress out that this term dB, it is not stochastic. It's completely deterministic, and because we know that b grows with the rate r, that's what it is. So we substitute all those terms into our replicating equation. We collect the terms. We get this equation. And again, there is deterministic part. There is stochastic part. So the only way for this equation to hold is this term to be equal to this term, and this term to be equal to this term. And that's what's written out here. So again, 2 equations with 2 unknowns, and here is the answer. Finally, let's take a s to another part, and notice that this part of our equation is completely deterministic, right? So we know how it will grow. So basically, d of f minus as, which is b times db, is r times b times dt. And we know all other terms. We substitute them here, take something to the left-hand side, and get this equation. So this is partial differential equation for our derivative f as a function of s and t of second order. And this equation is a famous Black-Scholes equation, which was derived by Fisher, Black, and Miles-Scholes in their famous paper published in 1973. And Miles-Scholes and Robert Merton actually received Nobel Prize for deriving and solving this equation in '97. Black was already dead by that time. And this is really the cornerstone of math finance. And the cornerstone is because using the replicating portfolio, using this reasoning, we were able to find an exact equation for our derivative. So a few remarks on Black-Scholes. So first of all, we made some assumptions on the dynamic of the stock, but we never made any assumptions on our derivative, which means that any derivative has to satisfy this equation. And that's very, very strong result. So if you assume that our stock is log normal, which is not a bad assumption and agrees quite well with the market, then we basically, in principle, can price any derivative. We know the equation for any derivative. The other thing is that our Black-Scholes equation doesn't depend on the actual drift mu in the dynamics of our stock. So again, it is the manifest of risk neutral dynamics. Not only we wrote down the equation for our derivative, we also found a replicating portfolio. So in other words, we found a hedging strategy, meaning that at any given time, we can form this portfolio with weights A and B. And if we hold both the derivative and both the replicating portfolio, altogether, this is zero-sum game. We know that no matter where stock moves, we will not lose money or gain money. So if we just charge bid offer on the derivative, if we charge a fee on the contract, we can hedge ourselves perfectly, buy the contract or sell the contract, hedge perfectly ourselves, and just make money on the fee. That's it. And finally, more mathematical remark is that actually, after a few manipulations, a few change of variables, the Black-Scholes equation comes out to be just a heat equation, which you already saw in this class. And this is very good news. Why this is good news? Well, because heat equation is very well studied. So the solutions are well known, and numerical methods, the ways to solve it, in particular the numerical ways to solve it, are well known. So we are in business. But as any partial differential equation, the equation itself doesn't make much sense, because to find a particular solution, we need boundary and an initial condition. And although any derivative satisfies Black-Scholes equation, the final and boundary conditions will vary from contract to contract. And here are a few examples of the final and boundary conditions. And here, an interesting remark that if usually we would talk about initial conditions, here we are talking about final conditions. The time goes in reverse. We know the state of the world at the end, at expiration, not today. So here are final and boundary conditions for call and put. And let's look a little bit at the pictures for our call and put to see where they come from. So for example, for call, well, this is our final condition, right, which is defined by the payout. On the other boundary conditions, well, what happens, we put them at 0 at an infinity. We chose that to put them at 0 at infinity. And why? Well, because if stock hits 0, then it stays at 0. That's what our dynamics shows. So the value of our contract at maturity will be just 0. On the other hand, if the stock grows to infinity, a good assumption to make is that actually it becomes similar to stock itself. So it just becomes parallel to the stock, and that's the conditions which we impose here. No. Similarly for the put, you can derive these conditions. And again, just because it is a heat equation, it turns out that for a simple derivative such that calls and puts, it is possible to find an exact analytic solution. And here are exact analytic solutions for call, put, and the digital contract. Well, not surprising again. I mean, they are all connected to the error function, to the normal distribution, basically as the solutions of heat equation ought to be. Why do they look exactly the same? If we have 5 minutes at the end, we'll probably shed some light on the specific form of equations. But let me just stress that we can see that it is discounted, and what I'm claiming is expected value of our payout under risk-neutral measure. And here is an example of a particular call option on the same IBM stock. So I chose a short-dated contract just to avoid the dividend payments. So it's a contract expiring on March 18th. So there is 10 days to expiration. The stock, as we saw, so this expiration, the stock, as we saw, was trading at 81.14. The volatility is somewhere around 14%, estimated either from other options or historically. And here is the price of our contract. And I also have a simple Black-Scholes calculator here, and let's see if we can match this price. So let's see what was. It was, I believe, the volatility was 13%, right? 1347. The interest rate, or it's already here, as we all know, Fed just bump the interest rate, so they are at 4.75% right now. The strike of our option was 80. Time to expiration was actually 10 days, and this should be measured as a fraction of year. So we divide 10 by 365, and this stock was trading at 81.14, if I'm not mistaken. And here is the price of our call option contract, which is 150. Well, it's within bid offer, right? So maybe our volatility is slightly off, and if we increase it to say, increase it to 14%, it will go slightly up. Yeah, 152. Well, in general, let's play a little bit with it. So, it is very short-dated option, so the value of our option is very close to the payout. So if we increase the time to maturity, let's make it 2 years, just to see better. So now value of our option is, well, that's what it is. And if we increase volatility, sure enough, let's make it 30%. So what do we expect? We expect if volatility is higher, the uncertainty is higher, so the value of our contract should go up. And it sure does. Right. Yeah, so basically that's how Black-Scholes works. And plenty of those contracts trade on the market. But unfortunately, not all of these contracts are so simple as calls and puts. Well, first of all, there are many more complicated products with more difficult payouts, which will constitute different and probably discontinuous final conditions on our Black-Scholes equation. Moreover, we made an assumption that the volatility is constant with time and interest rate is constant with time, which is certainly not true for the real world. Volatility probably should be time dependent, and this would make the coefficients in our Black-Scholes equation time dependent, and unfortunately this cannot be solved analytically. So in most of the cases in practice, we will have to use some kind of numerical solution. And finite difference methods is a typical approach for the heat equation. As you know, both explicit and implicit schemes, and you will discuss some of those in 1886. Three methods meaning that we go back to our one-step tree and basically assume that our time to expiration is many time steps away, and we'll grow this tree further. So from this node, we'll have 2 more nodes, and so on and so forth. Then you would imply the final condition at the end and discount back using our risk-neutral probabilities and get the price now. So those are called tree methods. And one can show that actually those 3 methods are equivalent to finite difference, explicit finite difference schemes. Those are very popular. But again, in tree methods, what is very important is to set the probabilities on your tree, the transition probabilities, to the right ones. And the right ones are risk-neutral probabilities, probabilities implied by the market, actually. Another important numerical method is Monte Carlo simulation, where you would simulate many different scenarios of the development of your stock up to the maturity, and then basically find using this path you will find the expected value of your payout. But again, in order for this expected value to be the same as the risk-neutral value, as the arbitrage-free value, you have to develop your Monte Carlo simulation with risk-neutral probabilities. So risk-neutral valuation is extremely important. And here is actually the general risk-neutral statement, which one can prove. is that actually the value of any derivative is just discounted expected value of the payout of this derivative at maturity. But you have to take this expectation at the right measure, using the right measure, meaning that you have to set correctly the transition probabilities. You have to make them market neutral. And under this measure, actually, the dynamics of our stocks looks slightly different. And as you can see, our drift becomes the interest rate. So under risk neutral measure, everything grows with our risk-free interest rate. And just to shed a little bit of light on how we got the solutions for calls and puts, Black-Scholes solutions for call and put. Well, this is the distribution of our stock, log normal distribution of our stock at time t. And if we take this distribution and integrate a payout of our call option against this distribution, in other words, find the expected value of payout of our call option under risk neutral measure, then sure enough, you will get to these formulas. And this illustrates the best, because what is digital? Digital is just the probability to end up above the strike at time t, right? So if you integrate this log normal PDF from the strike k to the infinity, that will be your answer. And this is a good exercise in integration to make sure that that's correct. So let's see, to conclude what we have seen. So we've seen that modern derivatives business makes use of quite advanced mathematics. And what kinds of mathematics is used there? Well, partial differential equations are used heavily. Numerical methods for the solution of these partial differential equations are naturally used. In order to get these equations, we actually need to operate in terms of stochastic calculus, meaning that we need to know how to deal with eta calculus, eta formula, Kirsanov theorem, and so on and so forth. The other thing is to be able to build simulations to solve the heat equation and all other equations which you might encounter. The topic which we didn't touch upon is statistics, because, of course, very advanced statistics is used for many things, for analyzing historical data, which can be quite useful for trading strategies and many others. And besides these 5 topics, there is much more to mathematical finance, which make it a very exciting field to work in, and that's what I wanted to talk about. And thank you very much for your attention. So
maybe I'll ask a first question about boundary conditions,
right?
Because you said that those are different for different contracts, and how do you deal with them in the finite differences or the tree model or whatever?
Well, what
would be a typical one?
Well, typical one. Yeah, here are 2 very typical ones.
Yeah.
So those you set them. You basically make a grid of your problem in particular, you build a tree, right, which is actually a grid of all possible outcomes. You set them up at the end. So your tree grows. So you set your boundary here at the end, and well, you set probably some initial this is final condition, so you set some boundary conditions here, right? So this is your time t. This is t0. This is time t. This is 0. This is 1. This is 2. This is t, right? So you set your payout here, so it will be maximum of s minus k and 0, right?
How many time steps might you take in a?
Well, well, you would do like daily for 3 months if it's 3 months option.
So 100,
something
maybe 100 steps.
Yeah, something like that.
Yeah.
Well, if it's a two-year option, that you probably would do it weekly or something like that.
So we
hundreds.
don't get into large,
No.
what would be scientifically large scale
No. In finance, you usually don't hit this problem of.
And in finite differences, do you use like higher order? Suppose you had second derivatives. Would you always use second differences, or I mean second order accuracy, or
in general, yes. In
Yeah.
general, second order accuracy. Yes.
Yeah.
In general, you don't go higher.
Yeah.
I mean the precision. Well, it's within cents, right?
Yeah.
So you can do better than that. So it depends. Well, it depends what kind of amounts you are dealing with. If you are actually selling and buying billions of stock,
Yeah.
you might consider something.
I see. Yeah.
Something more precise. But it's very defined. It's very problem defined. So yep. That's how we deal with that.
Any questions? You can put the mic on if you have a question.
This is a little bit inside of the topic, but can you solve it actually formulating the problem as a Markov process, a Markov chain? That you must have this other structure, right?
Well, it is Markov process. Yeah. I mean, this is just a numerical solution. So yeah, it is Markov process, and basically all stochastic calculus is about Markov process, a continuous Markov process. So we know process. Yeah, sure enough.
And is the mathematics that you get involved with pretty well set now, or is there a need for more mathematics, if I can ask the question that way?
Yeah, well, in this field, it is probably quite well set.
Yeah.
But if you get into more complicated fields, and especially into credit modeling, the model for the credits of certain companies, then mathematics is not quite set, because there you start talking about jump processes and not linear processes, not just log normal processes. And these stochastic differential equations become very hard, but maybe still analytically tractable. So from this point of view, there is need, but it's not a fundamental mathematics. Not that you're opening a new field, but definitely trying to solve a stochastic differential equation, which usually boils down to solving a partial differential equation analytically. Can be pretty hard in mathematical problem, purely mathematical problem.
And you showed us the example of a Black-Scholes solver.
Right.
Everybody has that available all the time?
Oh yeah, on Chicago trading floor, the traders have calculators where they just press a button and it's just hardwired there.
And they're printing out error functions, basically.
Oh,
some combination of error functions. Yeah.
That's all it does. Yeah. Well, sure enough, nobody uses just. I mean, this was very approximate example, and that's why I chose such short-dated stock that before it pays any dividend, and where we can assume that the volatility is constant, and so on and so forth to match the prices. Otherwise, the prices won't match.
Thank you, Master.
Thank you.